going, and then we're going to take a right angle departure from anything we've done before. So what do I have to do, ladies and gentlemen? I've given you the basic marching orders, and hopefully many of you will be able to pursue this. What do I have to do? Anyone? Okay, create a new model, right? Okay, we could call this SEIR transmission model ABM, and I'll say fall 2005. Great. The model time units will be days. Okay, good, days. Okay, so we created a new model. What do I have to do first? What to do first? I want to add a population of agents. Good. We have to create a new agent type. So how do I do that? Well, I can click here, new agent type, and let's add a person. Great. Okay. Now I want to lend this person an appearance. How do I do that? I want to give them an oval. How would I do that? Well, we can go down to the presentation area, and here we go, presentation. Let's give them an oval, and I'm going to drag it. Mark my words. I'm going to drag it here to their origin. Their origin is the place that if we drag it there, they will appear at the place where they're logically located. If we displace it, their appearance will be off-center from their logical location. So I want to locate them in a place so that they're, for convenience, that their logical location, their visual location are matched up. Okay, and so I've just done that here. This thing is a little bit off. So I'm going to go and shrink it again. Hey, come on. Another thing I can do is with the oval, I can scroll up and I can just set its radius to be 20, for example, which will cause it to have a there. I'll even set it to 10, and then I can center it nicely. Okay, and I could set its x value to be 0, and its y value to be 0 here. And we're off to the races. Great. So this is with person. Okay, ladies and gentlemen, I want to associate this person now with some location. Does anyone remember? Well, okay, first of all, we want to add a population. How do we add a population? Drag. Good. And we'll call this population, and we have to set what on it? Population of agents, right? Okay. So population of agents, great. Now, this is good. So we have this population of agents. We've set it here. And we want to make people appear at a specified point. So we're going to say in the specified point, okay? And the specified point will be drawn uniform 0 to 500. We could set it, and in other models we may set it to draw from other distributions. But right now we'll draw it uniformly from within that area, 0 to 500. Okay, so what did I do? Let's rehearse this. I went to person. I created a person. Within person, I dragged in an oval. I centered it at this location here, and this time I used the radius and these location areas. I then went back. I went back to main. I dragged in person to main to create this population, but to make it an actual population rather than a single agent, I selected population of agents. I let it be the default. For the initial location, I said at the specified point, and I did uniform 0 to 500. Okay, so if I run this, what will I see? What should I see? Everyone scattered. Good. Okay, now, riddle me this. Suppose I wanted to specify to this model as a whole the number of people to have in the population. How would I do that? Well, you've done some agent-based modeling some system dynamics modeling in AnyLogic already. How would I capture, say, a contacts per day within a system dynamics model so I could vary it in different experiments? Using a parameter. So we want a parameter here. So we'll go to parameters and we'll drag it into main. Mark my words, into main. So this will be called population size, yeah? And what sort of parameter will it be? What's its type of that parameter? Is it a double? Is it a string? It's an int, indeed. It is a count of discrete possibilities, all right? Int, there it is. Okay, great. Okay, so now, in order to complete the thought, what do I have to do? I have to have the initial number of agents be set to be given by population size. Okay. Does anyone need help? Okay. Questions? So an integer, it'll be an integer count of people, and the initial number of agents in the population will be given by, I said population size. Should be population size, okay? Build early, build often. When you complete a logical chunk of work, build. And in software engineering, you complete a logical chunk of work, you can test. If it's a larger chunk of work, after you test, after you document, maybe you have it peer reviewed, you can check in. Okay, great. So we could have a simulation here, and we'll have a population size of 100 for a base simulation. Let's add a new experiment with a population size of, we'll call it large population, and we will give it a population size of 1,000. Okay, great. Population of 1,000 here. Boom. There we go. You see that? Okay. Okay, great. Okay, so we have this model. Its population size is adjustable. We have person. Now let's get down to business in terms of the dynamics. We want to construct a very similar state chart to last time, but we are going to do this in a slightly more principled way. Okay, so what do I need to start the state chart? State chart entry point. So let's call it infection state chart, okay? In general, we could have multiple state charts. We could have one state chart, say, for someone's infection status, another for their attitude, another for their employment status, another for their status with respect to vaccination or what have you. Susceptible, infective, and recovered. Okay? Okay, great. Recovered. Okay? Maybe for good measure, we will go add another category, to which we'll add a category of exposed. These are people who are latently infected. They don't know, they don't have symptoms perhaps yet. They're certainly not infective yet, but they are infected. So we call them exposed by tradition. Exposed. Okay? Actually, it should say exposed. Okay. And there's some latent time that they remain there. Okay, great. So we need to hitch up these states. So let us go drag in some of these transitions, and we will go and successively name and successively set the rules by which the transitions fire. So I'm going to drag this back here. Note, if I want to route this transition around for aesthetic reasons, it doesn't affect the logic of the model. If I want to drag it around, I could double click on the transition and I can pull it in different ways. And it will allow me to sort of shape it as I see fit. So you drag it out here and down here, and we can have a nicely rendered components. Okay, so we're a lot of the way through. We've basically characterized actions and states. Now we have to specify the rules. And to specify these rules, ladies and gentlemen, we're going to do this in a slightly more principled way so that I don't need to twitch as I'm teaching you. So let's go to main. Well, okay, so let's first reflect on something. I want the amount of time someone spends in an exposed state to be dictated by a parameter. Okay? So it's going to be a parameter that specifies how long they're in the state before they become infective. For something like flu, it would be about 3 days, something on that order. So how could I do that in a way that would allow me to change it? Say, change it for different experiments, change this assumption. What would I need to put into the model? I could hard code it, for sure. I could make it a timeout with a timeout of 3 days. But that's going to be pretty inflexible. Every time I want to run an alternative scenario, I have to come and modify this value. That's not the sign of a robust way of building models. Among other things, you may come in and change it to some value, you run it, and you forget that you changed it, and it's here, it's hidden. It's very nice if we could specify them differently for different scenarios, different experiments. And we say, for this experiment, we want these assumptions. For this other experiment, with these other assumptions. How could I do that? Based on what we've learned, how could I encode that assumption? With a what? With a parameter. Good. Okay. So that's the first step. But let's take this one step further this time. So let's draw in a parameter. We're going to have mean latent time. Okay? Good. Mean time in this latent state, this exposed state. Okay, great. And we could go here, and we could refer here to a timeout to be what? What would we do? Mean latent time. Great, great. Okay, we're in good shape, but the problem is, if we go to our experiment here, let's go to our experiment. There's no value we could fill in a value for population size, but not for mean latent time. Why? Because that's a property of the person. Parameters, mark my word, ladies and gentlemen. Mark these words. Parameters do two things. They encode an assumption, number one. But secondly, they communicate that assumption from the point where something is created to that object. So persons are actually created most directly by this population. And so it is in the population, the point of the creation of this thing, the person, where we specify the value of the parameter that lives in that person. If, by contrast, we had main, which has a parameter, which it does, population size, the thing that creates main, it turns out, and this will feature strongly in later lectures, is in fact the experiment. And so that's where it's specified there. So mark my words, a parameter encodes an assumption and communicates that assumption from the point of creation to where it is used. Okay? And the point of creation of main is the experiment, and therefore that's what encodes the parameters. Point of creation of persons that we're going to concentrate on this lecture is at the population, and that's where this needs to be specified. So we could do that. We could specify it, but it still wouldn't let us vary it easily for experiments. Now, we have two unpalatable choices, and both of them rub me the wrong way. One thing is we could add a comparable parameter in main and use that to say the default value of mean latent time and use it to communicate to all the agents. Or another unpalatable option, we could take this parameter out of here and we could put it in main. Hoist it up to main. And that, ladies and gentlemen, for the sake of expedience, because the minutes are counting down, we will do. So click on this parameter and we will cut it and we will indeed paste it into main here. And Alan, stand ready. Okay? Okay, mean latent time. So it's now in main. If we build our model, it will be an unhappy camper. Why will it be unhappy? Well, this thing was referring to something that was in person, but now it's in main. So what do we have to do? We have to say main dot mean latent time. Yes, there's an implicit variable called main, which it can use to refer to it. And if you want to be very precise about it, it's this main variable lives in this, in the current person. This dot main latent time, or you could just make it main dot mean latent time. Okay, great. we will go through a similar process, but putting it directly into main for three other parameters, to wit, mean recovery time, and mean time until waning immunity. So let's go apply ourselves to this task. Mean infectious time, yeah, that's good. And then finally, mean time until waning immunity. Each of them is a double precision value, and they all live, ladies and gentlemen, in main. Okay? Mean latent time, mean infectious time, mean time until waning immunity. Does anyone have a question? Does anyone need to secure Alan's able services? Okay? Okay. Build early, build often. Make sure the model's proceeding well. And now, ladies and gentlemen, once you finish that task, we will go back to person. And in person, we will now make use of those parameters. We have already made use of this parameter going from exposed to infected. In the infected state, and we have made that a timeout. In the infected state, by contrast, we will use a rate transition, mark my words, a rate transition, and we want that person to remain in that state for an average of mean infectious time. How would I put in place a rate so their mean time in that state is mean infectious time? Anyone? 1 over it. 1 over main dot mean infectious time. Good. Okay? That's a double. So I actually don't need to even put 1.0. I could just put 1, but it's good to be careful about that. Great. And that reflects the fact that actually people vary quite a bit on how quickly it takes them to get over something like the flu. Okay? And mean time until waning immunity, this also will be, say, a rate transition with a time which is given by 1 over the mean time until waning immunity. Okay? Great. Now, I'm going to ask you this. This is a practical question. I just want to test your feelings. Okay, so right now, the time that someone spends in this exposed state is given by what parameter? By mean latent time, no less. Correct? Indeed. So this is set to be a timeout. And I set these others to be rate transitions because I said there was some variability. But suppose we wanted. So when I say there's a rate transition, there's some variability. When I say there's a rate transition, well, okay, let's think about this. And I don't want to spend too much time on this because time is a ticking, but it's a useful point conceptually. Ladies and gentlemen, if I were to graph out, so over here on the right-hand side, on the right exhibit, I show a probability distribution for how long, so we call this the residence time, how long someone will spend in a given state for a rate transition, right? Hello? Yeah? This is a probability distribution? This is a probability distribution. Yes, this is a probability distribution. This is only a probability distribution. You're too young for that. So Alan remembers that probably. This specifies the probability that someone will spend a certain amount of time in a state. And this is what it looks like. It's called an exponential probability distribution. And it's associated with the situation where you have a certain probability per unit time of leaving, certain hazard rate, exponential distribution. Its residence time, we say, is exponentially distributed. This is called an exponential distribution of residence time. And that's what it looks like. if I tell you you have a 2% chance per day of leaving, it implies that my time spent in that state is exponentially distributed. If I'm still in the state now, my chance of leaving the next day is what? 2%. About 2%. Because it's continuous, it's slightly different than that, but slightly lower, but because it's continuously compounded. But yes, it's about 2%. And the next day, I've exactly that. If I've been there 10 days, what's my chance of leaving in the next day? 2%. If I've been there 100 days and I'm still there, as long as I'm still there, what's my chance of leaving the next day? 2%. It's a fixed. No matter how long I've been there, I've got the same kick of the can every day, the same chance. The probability of leaving conditional on still being there is flat. But the chance that I will have left in the first day is a lot higher than the chance that I left in the second day, than the chance I left in the third day. Why is that? Why? Yeah, I mean, so you know, I'm sure to be there at the beginning of the first day, right? And so I have the 2% chance of leaving in that day. 2% in that day. So, you know, I have a higher chance of leaving in that day than I will of having left in the 100th day. Because after all, I might have left in the first day, the second day, the third day, the fourth day, all these days up to 100. So my chance of having left in the 100th day is actually a lot smaller than the chance of having left. So the chance of having left in the 100th day, somewhere out here, is much smaller than my chance of having left in the first day. Do you get that? But if I'm still there, if I know I'm still there, my chance of leaving the next day is 2%. You get that? That's what a rate transition is. That's associated with a rate transition. And it implies a residence time distribution, a chance of having stayed there a certain amount of time before leaving that is exponentially distributed. It's like this. Grok or not? Grok. Okay. Now, how about a timeout distribution? What do we got there? What's its residence time? How long do we spend there before we leave? That exact number. So its residence time, the probability of leaving in the first, let's suppose that we're considering a residence time of 3 days. What's the probability I leave in the first day? 0. Probability in the second day? 0. Probability of leaving after exactly 3 days, on the other hand, it's 1. You know, I am leaving after exactly that amount of time. So what's my probability of leaving on the 4th day, the 5th day, 6th day? 0, right? So it looks something like this. The probability of, okay, I said remaining in the state, and equally much so, I could, to make this comparable, I'll say the probability of leaving at that time. Either one is actually exponential. Probability of leaving at this time, is, it goes like this, 0, and then it's 1. And then it's 0. Okay? The probability density, it's actually, if we're dealing with continuous time, this is actually a Dirac delta function. Does anyone know what a Dirac delta function is? Anyone heard? Yes. Good, thank you. So a Dirac delta function, I don't want to scare the computer scientists in the audience. Continuous mathematics is, it's an interesting beast. And basically, we're dealing with probability densities, my chance of leaving in the next unit time. And here, you're leaving it exactly at an instant. And so it turns out that this is, at that instant, the density is infinitely high, and it has to integrate up to 1. But never mind about that. The effect is, I'm sure to leave at exactly that day. Whereas in this case, I'm actually more likely to have left in the first day than the second day than the third day. Here I'm exactly leaving at that day. Does that make sense? Okay, now, here's the practical issue. Here's the practical issue of this. Suppose I wanted, this is with a fixed timeout, right? Fixed timeout. right? Okay. I should tell you, this guy here on the right, this guy here, we call this a memoryless process. I'm trying to figure out where to write it. Try to figure out what color to write it. I need to emphasize this. Watch this. Mark my words. This is a memoryless process. I got to make this big, bold, and red. Memoryless process. Memoryless process. Why do I call this a memoryless process? Same kick of the can no matter how long I've been there. It doesn't matter if I've been there 1 week, 1 day, 1 nanosecond, 1 year. I have the same 2% chance of leaving the next day. Do I not? For this? 2%. That's what a rate transition is. 2% chance per day. 1 over 365. Do the math, whatever it is. 0.003 or 002 something. It's memoryless. No matter how long I've been there, it's the same chance. It's this. You see that? That's memoryless. Is this guy on the left memoryless? Is this one memoryless? Is it independent how long I've been there, my chance of leaving the next day? No, it most certainly is not. This is not memory. This is like memory full. You leave it exactly this time. My chance of leaving, it sure as heck depends on how long I've been there. My chance of leaving in the next day or next half hour or what have you depends hugely on how long I've been there. It depends exactly on how long I've been there. It depends only on how long I've been there. All that is needed to specify is how long I've been there. If I don't know that, I don't know anything about when I'm going to be leaving. Okay? Does that make sense? So this is what we call, now people, some of us call it memory full process. It's not memoryless. You can call it not memoryless. People don't like that either. Can't make everyone happy. It's memory full process. It's not memoryless. This is memoryless. Okay. That's an important distinction. That's a testable distinction. That's an examinable distinction. That's a practical distinction, it turns out. Okay, now, the practical consequences are as follows. So suppose I wanted to have my amount of time spent in this latent state not be drawn from one of these distributions, but I want it to be variable in some way. Maybe I want it to be drawn from a different distribution, not this one. I don't want it to be exactly 7 days. I don't want it to be exactly 3 days. I don't want it to be drawn from this exponential distribution. I want it to be drawn from something else. Maybe I want it to be drawn from a beta distribution, or I want it to be drawn from a Gompertz or a Weibull or a log normal distribution or what have you. I'm not going to worry you about all the details of it, but I have some distribution. Maybe it's an empirical distribution from data that I actually have that say some people recover in different amounts of time, and it looks something like this with a long upper tail, and it's 3 days, and the minimum is somewhere around 2 days, and the maximum is somewhere about 5. How could I do that in AnyLogic? How could I do this using this mechanism? Anyone? How would I do that? So it seems right now that we're stuck between two things, by appearances, by facile appearances, by superficial appearances. It appears that we're stuck either with a rate transition that imposes an exponential distribution. We don't have much choice about it. We had to live with that for system dynamics because that's the nature of the beast. But alternatively, we seem to have this fixed time transition associated with timeout. But it turns out that this is a flawed dichotomy. Why is that? Here we have this timeout. Why do I say it's not truly a choice between these two extremes? Because there is another alternative, and it's not even just another transition type. Ansgar?
I was going to suggest that what you drew there reminds me of a normal distribution.
Sure.
And you can describe a normal distribution with its mean and its variance.
Good.
So we could just describe these two derivatives and then...
Good. Yeah, so that's right. It looks a little bit like a normal distribution. One has to be careful with normal because they can go negative, and you'd have to take a minimum. But what we can do, you have the kernel of the idea. Unscar is exactly bang on. I mean, folks, we're in 394, 858. We don't have to live with a constant. We could do something like draw this from a normal distribution, right? Now, for those from statistics background, you'll be deeply disturbed to know that the normal distribution within AnyLogic first requires the sigma and then the mean, which disturbs me greatly. But, so maybe it has a sigma, a standard deviation of 0.5 and a mean of 3 days, right? We could do this. I mean, so when someone enters this exposed state, it's going to draw from this distribution, from this normal distribution with this mean. And really what I'd want to do is I'd want to take the maximum of this and 0, so I don't get a negative value. Or I would use another form of normal that it provides. There's many forms of normal it provides, and one of them provides, I think, a minimum for it. Yeah, there's a minimum here. So I could do that. But the point is, ladies and gentlemen, this is a false dichotomy. It's not that we have to choose between these two extremes. We can take this maximum basically would draw from the normal distribution, but if the value from the normal distribution is below 0, it would use 0. Something like that. The point is, with a timeout, we have full choice as to what distribution we want to draw it from. If we want to draw it from some empirical data, from a custom distribution, I would highlight the fact that in AnyLogic, in the palette, no less, in this area of the agent, there's a custom distribution. You can just drag it in, put in some values there that define a custom distribution that has a certain probability of being in a certain interval, and you could draw from that distribution. So a timeout will support arbitrary distributions. Now, I don't emphasize this for no reason. First of all, it's very important to realize that with stocks, like a first-order delay, and with rate transitions, we're dealing with memoryless properties if we have a fixed rate. And in fact, in system dynamics, in an aggregate model, as Dana referred to earlier, if the rate cannot depend on how long someone has been there. The stock is viewed as well mixed. It's independent of how long you've been here. If you need to keep track of how long you've been here, you need to divide up the several stocks. With a rate transition, we could actually have that rate vary by how long a person's been in that stock by cleverly designing it. And we'll see that later in the class. But the point is, by default, this is memoryless. This one is memory full. But we can, in general, capture other memory full distributions, like this one here. Anything except an exponential distribution is memory full. But we could choose our own memory full distribution. We're not limited to doing exactly some period of time by putting in a draw from an appropriate distribution, including, I would say, a custom distribution if people are interested in it. And I'm not going to fill it in here, but you could see you can fill in frequency tables or observed samples or ranges, and you could draw from a continuous distribution or a discrete one, etc. Okay, so I just deleted that custom distribution because I want to finish this example with some key components. Okay, so having done this, ladies and gentlemen, I would like us to go back and let's go back to main, and we're going to put in, for simplicity, we're going to put in some parameter values for mean latent time, okay? We're going to, for each of these mean values. So default for mean latent time will be 3 days. The default for mean infectious time will be 7 days. And mean infectious time would be 10 days. And the default for mean time until waning immunity will be 270 days. Okay? So mean latent time, 3 days. Mean infectious time, 10 days default. and 270 for mean time for until waning immunity. Okay, ladies and gentlemen, what this means is by filling in those defaults, each of these experiments will have default values unless we change them for those parameters. Okay, great. So the final thing we have to do, though, is the job to which we will turn our attention right now. And that has to do with, right now, this is a fixed quantity, right? This transition here, 1 day from susceptible to exposed. So if we run this model, how will people progress? Well, we could go see. Here we go, and let's go to a large population, sure, and we can go run it, and what we will see if we go down to a given person is this person proceeds among these states over time, and they are whipping among these states. They spend a lot of time in the recovered state and a little bit of time in the susceptible state because we have a mean time to getting infected of 1 day. Okay, so quickly here, time is of the essence. I want to add a color so that we indicate the infection status of the person. How do we do that? Ladies and gentlemen, drag a variable and call it color, lowercase c. The type of it is what? Capital C color, indeed. And its default value will be black. And we will assign it in the susceptible state to be green. Great. The exposed state, we will assign it to be orange. Say yellow. Sorry, yellow. Okay. We will assign it in the infective state to be red. Oop. Color equals red. We will assign it in the recovered state to be color equals gray with an AY. Okay, and then how do we complete that logical chunk of work? What do we still have to do to make that color actionable, to make it operational? What do we still have to do? Okay, we've just set color to be green, yellow, red, and gray. What do we have to do? We have a variable called color, lowercase, with a capital C type. How do we actually make it operational? Yeah, we set the oval to depend on the color. So go up and click on the oval, go down to fill color under appearance, and set it to depend on color. Okay? Great. Color. Excellent. Ladies and gentlemen, it's now set on color, okay? Now, let's run this model. What should we see? Build early, build often, make sure it's a happy camper. Alan, prepare for deployment. Okay? Okay, you should see something like this. The very first start, it started, okay, Alan, sector 1. We should see it whipping through a bunch of states. Do you see something like that? Yeah? Okay, ladies and gentlemen, now we're going to perform the coup de grace that will be essential for your problem set. So watch very carefully my actions here. And Cam Studio is happily recording. Okay, so we're going to undertake 2 steps here. Okay? Actually, 3 in total. Step 1. Okay? We're going to change this transition from susceptible to exposed to depend instead on a message. Messages provide the way that agents communicate with each other. Okay? Okay? So when an agent comes into contact with another agent who's infective, that agent will be sending messages. And if the agent who receives it is susceptible, if they receive such a message, they will transition to the exposed state. In other words, they will get infected. Does that make sense? Okay. Think of that message as like a message, you've been around someone who just coughed, and that person is sick. A sick person has just coughed. Okay, so that's step one. We changed this transition from susceptible to exposed to be based on a message. Step two here, Alan, is there? Okay, so for Ansgar's sake, we just changed this transition from susceptible to infected to be a message transition. Okay, when two people are when an infective is infective, they will be sending out these messages to others, and those other people get infected. Okay, step two, we are going to add a transition from the state chart area, a transition into the infective state, which will allow an infective person to periodically, with a certain rate, we'll call this transition a contact, with a certain rate of contact, say 5 per day, they will come into contact with others around them. Okay? And initially, we're going to set the action here to be this dot send to this will be send to random, and we're going to send a message, infect or exposed, exclamation point. In other words, you've been exposed to the bug. Now, some of the people who receive it may be already in the exposed state or recovered state or the infected state, and they'll ignore the message. There's no transition from those states to handle that message. Where this transition does occur is from susceptible. So if someone who's susceptible receives the message, they will get infected. Okay? That was step two. How did I do that? I went and added this transition. The transition is on a rate transition called contact, rate of 5 per day, and I just put into place this send to random. Hey, send to random. Okay, expose. This is the text. Okay? Are people okay with that? The minutes are ticking. Are we okay? How many people would like a little bit more time to catch up? Okay? Okay. The final thing we're going to do at the moment, and then we'll make one more pass, is we're going to go up to main, and we will actually, in main, have it send off a message to infect the first person. So if you go to main, there's a thing that says on startup. We could do it this way, and I think we will do that. We could put it in on startup. Alternatively, and I prefer this way, if you go to the agent palette, drag an event into main, and this will be initial infection event. This will be an initial event. It's a timeout. It occurs one time at a time of 0 days. And there will be an action associated with it. And I would like to set this action for this event, this initial infection event, will be this dot deliver to random agent inside. And again, it will be a message exposed, exclamation point. Okay, so it's going to deliver to a random agent within main a message that says exposed. Why do we have to do that? Suppose we weren't to do that. What would happen? Nobody would be affected. Exactly. No one's initially infected. Okay, so how did I do that? I went to main. I went to the palette. I went to the agent area of the palette, and I dragged in an event. And all I did is I came down here. This event will go off at time 0. And I put in the action this dot deliver to random agent inside. Are people okay with that? Okay, now, ladies and gentlemen, let's run this model. So I'd like you to do run the simulation, and what do we see here? What's going on now? I'll start it again from the first. Why does it stay yellow for a while? Anyone? Why is this just yellow? Yeah, it's not infective yet, right? It got infected, but it's not infectious. It's still in the what state? Yeah, it's in the incubation. It's incubating. It's in this exposed state. Okay, and now it continues on to be red, and now it can infect others, and now these are infecting the others. But, ladies and gentlemen, now we're going to do the final step. Do people see that? Who needs Alan's help? Alan stands ready. We're going to now complete the final component that will be very useful for your problem set 3. We've already done some of it. But, okay, ladies and gentlemen, I'd like you to go to main. And I'd like you to go in main down to this area we've never really used before, to my recollection, space and network area. Okay? Do you see that? Space and network in main? Do people see that? Okay. Go down to space and network. Ladies and gentlemen, I would like you to set a network type to be distance-based and set it to be a distance of 75 units. What this means, ladies and gentlemen, is that if two individuals are within 75 units of distance of each other, and we can set what that means in meters or kilometers through a separate interface within AnyLogic, but if those people are within 75 units of distance, they will be connected with a network, otherwise not. Is that okay? So connection range 75. Next, and this is important. Okay, is that a question over there? No. Okay. Okay. Did people follow that? Main, go down to this area, space and network. Go to distance-based connection, distance range 75. Did you get that? Okay. We're almost done. Almost done. We've just got 2 more steps. Firstly, I would like you to now go to person, and we will go change for this contact transition. Mark my words. This will be very important. For the contact transition, where we have had to this point, this to send to random, I'd like you to change it instead to this to send to random neighbor. Excuse me. Send to random connected. Excuse me. I stand corrected. Send to random connected and send the exposed message to them. Right now, the contents of this message actually don't matter. It'll handle it. Send to random connected. Is that okay? Okay, so what did I do? I went down to person. I went to this transition here in effective, and I set the action to this to set to random connected exposed. Are we okay with that? Yeah? Okay, ladies and gentlemen, I'd like you to run the large population. And I'd like you to tell me what you see here. What do you see? What's different from before? Do you see that? This sort of thing? Okay, what's happening? It's spreading over a network. But where's the network? That, ladies and gentlemen, is the final thing we have to do. The network's there. It is spreading over that network. Why? Because we set this contact to now do send to random connected, not to send to anyone, but to send to one of my connections in a network. But we can't see the network yet. Let us now see the network. You want to see the network? Okay. You're going to see the network. Okay. Within person, scroll up to where you see connections. Do you see this? You have to scroll up. You won't see it initially. You have to scroll up here. There's a thing called connections. Do you see that? Okay. I want you to select that. We're down to the last minute. Scroll down to where it says animation. and I'd like you to check the box that says draw line connecting agents. Do you see that? So what did I do? I went to person, I scrolled up to see connections, I scrolled down in connections to this area, draw line connecting agent, and I checked it. Are you okay with that? And now, ladies and gentlemen, I would like to run this scenario again. And you should see something like this. There are connections between these agents. Okay? And now you can start to see them propagating. Ladies and gentlemen, I'd like you to go to your original simulation here. And I would like you to watch this. We had a population size of 100. I would like you to go do this for that, and I'd like you to run that. And you will see it spreading on the network. Do you see that? Alan stands ready, stalwart in the back, ready for any needs. Okay, are you people good with that? Ladies and gentlemen, I deliver you to problem 3 at the problem set, which exactly uses this mechanism. And you'll have about a week's now and extended time to complete this. But that will draw directly on this exercise in many of its details, in putting in place a state chart, in having in place these mechanisms within the state chart to receive messages. This message here, notice it was unconditional. We didn't even pay attention to the contents of the message. Later we could, if we could have a spread of HPV and of HIV, we'd have different messages. We had here a situation where when someone's infective with a certain rate, they're contacting each other and they're sending messages to the person they're contacting. Within Maine, we had associated with this population, we had people placed in a distance-based network where they're connected with, if they're within a certain range of each other. A given pair is connected if they're within 75 units of each other. And that allowed each person to not only get into this infective state, but they had connections to others who are nearby them in space. And with each of those connections, they will have a chance of infecting them when they themselves are infected, because in this infective state, they're having 5 times per day, on average, they're sending this message, basically sneezing around or coughing around one of these neighbors around them within this network. They may have lots of connections, in which case, each of those connections has a comparatively low probability of getting exposed in a given one of these, or they may have one connection. It's always that person who keeps on getting it. But they're sending it to a random connected. Okay? Are we good? Okay. So that's a good start. That should put you in good stead. Thank you for your patience. Do remember this material up here on memoryless versus memory full processes. And I've also provided a video that I'd like you to watch for Tuesday. Thank you very much. And I will